Muito bem. So for me, it's a great pleasure to introduce you David Wineland. David Wineland is being one of those scientists that has tasted basically all the flavor of metrology in the world. He worked with Norman Ramsey, and then he worked with in Seattle with Demelt in ions, and then he established himself at NIST in Boulder. And we all know that that laboratory is the most prestigious and prominent laboratory in the field of trapping ionized particles for the purpose of understanding the atomic nature, and also to understand and use trapped ions as elements for metrology, and most recently also for demonstration of quantum computation operation. And if you have to be in this field, you know David Wineland. If you are not in this field, you also know David Wineland, because it's almost impossible to speak about controlling atomic species without getting into his work along many years. And I have the pleasure to visit his lab once, and is really one of the examples of how should we go in this field. So he's gonna present us with a general talk about Schrödinger cats, with there is no cat in here, the people in biophotonics. We're not gonna open a cat or treat PDT or anything. But he's gonna show how quantum mechanics influence macroscopic world and everything, and that's a very fundamental.
Yeah, thanks, Vanderlei, for your generous introduction. Everything will be a letdown from here now. So what I wanted to start off this talk about, which is more or less basically about this new subject of quantum computation or quantum information processing. And a way to introduce it goes way back to 1935, when just after the invention of quantum mechanics. I'm always impressed because Schrödinger, who was really one of the inventors of quantum mechanics, was in some ways was distressed by its consequences. And one of those consequences is that we know that quantum mechanics in fact works extremely well to explain our physical world, particularly on the small scale. But the strange thing about quantum mechanics is that it also predicts that, I mean, it should work for large systems as well. And the thing that distressed Schrödinger was that he explained his worry in terms of this example of his cat. So just to recall, so the example of Schrödinger's cat was, he supposed you had a sealed box here, and that's important in the end, but we'll assume that we have an isolated system, this cat in this box, and also in the box is say a single radioactive particle, and there's some mechanism that if the particle decays, then it triggers a mechanism which releases poison and kills the cat. Well, of course, it would be tough to do this, but in principle, we could write down the equations of motion of this system. And what we find is that what quantum mechanics tells us is that the only thing we can say after a time equal to 1 half-life is that what quantum mechanics predicts is that we end up with this wave function where there's an equal superposition of the particle not having decayed and the cat alive, and also an equal component of the particle decayed and now the cat dead. And so in a sense, all we can say is that that's all that quantum mechanics tells us. So the way we resolve this, of course, is that we inject this idea of measurement, and when we measure the system, this wave function collapses so that with equal probability we find the cat either dead or alive, not alive and dead at the same time. But the curious thing is that quantum mechanics tells us is that before this measurement, the system exists in both states. The cat is both dead and alive. The other thing is that I'll touch on throughout the talk is this idea of entanglement. When we write a wave function like this, we see that the properties of the particle are correlated with the cat being dead and alive in this case, and that'll be a theme that reoccurs through this idea of quantum computation. So with that, just to summarize, I'll give some examples. Of course, we haven't been able to realize Schrödinger's version of this superposition state, and we probably really don't want to, but we can start to make very small examples of this Schrödinger cat. And I'll try to say how this applies to this newer idea of quantum computation. And of course, a useful quantum computer is far in the distance, but we can start to do some of the simple steps that we need to make a quantum computer with atoms. I'll also say, since I think Vanderlei in his introduction mentioned, I'm at the NIST, National Institute of Standards and Technology in the US, and the main business of our group has always been to make atomic clocks, and I'll try to say how we're able to use some of the simple ideas of quantum computation and apply them to metrology, in our case, atomic clocks. So just to give you an idea that this business of quantum computation, I show our group here. This includes the present members and some recent past members here. So our two main projects are working on this idea of quantum computation and also atomic clocks. We're just one group, however, that are pursuing this idea of quantum information processing. So I list at least all the groups I know about currently that are working on just using atomic ions to try to address this problem of quantum computation. And of course, there's a whole host of other possible physical implementations that people are looking into. I'll mention just another example later on of other systems that are used. But this, just to give you an idea of the scope of this field now over the last 10 years, these are just the groups in using atomic ions to try to realize these things, but there's a large array of other groups working on similar problems. So if we go back to Schrödinger's cat example, here's a bit more humane version of one. Suppose which has the same properties. Suppose we think about a marble in a bowl, and the marble can roll back and forth in this bowl. And we somehow have attached an atomic particle to this marble, and you can think, for example, about an electron that has two states with a spin oriented up or down. And we've attached this electron to this marble. Well, a case that mimics the Schrödinger's cat is where, as this marble rolls back and forth, at some instant of time, the marble would be on the left side of the bowl, associated with a spin pointing up, simultaneously with it being on the right side of the bowl and the spin pointing down. Well, we can't yet do this even with a marble, but we can do this on a microscopic scale. And what we can do is we can associate two states of an atom with the position of the atom in what we call a trap. I mean, it's like the marble in the bowl. And the reason this mimics the Schrödinger's cat is that we can, like the radioactive particle, we can associate the microscopic aspect of Schrödinger's cat with the state of the atom, the internal state of the atom, and the more macroscopic property, like the cat being dead or alive, is associated with the atom being on the left or right side of the bowl. So in our realization of this very small cat, you might call it a kitten, is that we're able to realize a situation where our atom, in this case a charged beryllium ion, is at some instant of time is both on the left and right side of the trap, where the position is associated with different states of the internal state, the spin. And this is of course, a very small version of Schrödinger's cat, where only these two parts of the wave function are only separated by about 8 times the spread of their wave packet. So you might say, well, this is too small to call a Schrödinger's cat. And the problem, if you say it's too small, then you have to say, well, where's the dividing line between small and big, where you might call this a Schrödinger's cat. And the problem, I think, is that nobody can really say where that dividing line is. So this really does have aspects of Schrödinger's cat, even though it's a very small one. So let me now jump to this idea of quantum computation, and I apologize, I can only give you a flavor for that. It would take several lectures to really introduce this idea of quantum information processing, but I'll try to give you some of the elements here. And one of the elements is that one of the nice aspects for experimentalists like myself is that we don't really have to know a lot about algorithms in order for us to be useful to try to make a quantum processor. All we need to do is to be able to do 2 things. And in an analogy with a classical computer, the PCs on your desk, for example, in principle, all we need to be able to do is 2 things. So a classical computer could, in principle, be composed of just two gates. One is a bit flip, and it doesn't have to be this combination, but the other could be, say, a 2-bit AND gate. And although it may not be the most efficient way, with these 2 gates, you could form a universal classical computer. In an analogy with that, in the quantum world, we also need to be able to just provide 2 operations, and they could be different than the ones, somewhat different than the ones I'm explaining here, but this gives the basic idea. That is that we can compose a universal quantum computation, that is any quantum computation with a combination of these 2 gates. So the first one is an analogous to the bit flip, but in this case, what we want to think about is a rotation, and the picture you want to have in mind here is that, say, for a spin 1/2 particle, it just says that we're not only able to, say, take the spin 1/2 particle from its eigenstates up and down, but we can also rotate the so-called block vector associated with those states. We can rotate to any position on the block sphere. And this, of course, we've been able to do in atomic physics for at least the last 50 years, these sort of coherent rotations of this block vector representation. The other thing which is a little harder is to make some sort of gate between 2 quantum bits. And in this particular example, this is called a pi phase gate. In other words, this minus sign can be represented as e to the I pi, a phase shift of pi. So when applied to eigenstates, this looks like just like a classical gate. It looks like an XOR gate. It's not a very interesting gate, but when applied to superpositions, as I show down here, it leads to this property of entanglement. That is, if we have 2 qubits in equal superposition states, when we apply this logic table, we get this state down here, which is no longer a separable state. That is, the quantum properties of these 2 quantum bits is now entangled. So, okay, so here's about the last part I'll say about quantum computation in general. But the reason for saying a little bit about this factorizing algorithm is that around 1995, Peter Shor, a computer theorist, came up with an algorithm that said that if you could make a quantum computer, you could efficiently factorize large numbers. And of course, the reason this fueled a lot of research, certainly in the United States, the the intelligence community was very interested. This is the heart of their business, because basically the single most common algorithm for doing data encryption derives its security from the inability to factorize large numbers. So if we could factorize large numbers efficiently, basically it would compromise all encryption schemes. So they're very interested in this. So they've been the primary funders in the US anyway for this type of work. So I'm going to try to give a flavor for some of the elements that go into this factorizing algorithm. And one thing to think about, this is a crude analogy, but it kind of gives the idea. If you think about, if you're trying to factorize a large number, which is, say, the product of two large prime numbers, what you can think of, there's a certain periodicity. That is, one of the factors essentially repeats a number of times equal to the other factor. You can think about this larger number that way. So what this algorithm does is it basically is a way to find this period, this repetition of the first factor to give the larger number, which is the product of the two numbers. And one way to think about this quantum algorithm is it's like an interference experiment. What we do, in fact, in this algorithm is that the input state is we take a number of qubits, which has to be at least as large to represent the number we want to factor. And then what this algorithm does, which can be just a series of these simple single and 2 qubit gates, is that it provides kind of an interference of the wave function of all these particles. We make an equal superposition of all the states that represent that number. And in fact, what we do, one of the aspects of quantum computation is that this equal superposition that we plug into our input register represents all the numbers in this number we're trying to factor simultaneously. And what this algorithm then is provide an interference, whereas so that at the end, when we measure the state we measure, of course we know by the projection postulate that when we measure, we only measure one state out of the 2 to the n possible states that we've put into this algorithm. But it turns out that Peter Shor he showed that the state that you measured then could be used in a classical algorithm to derive the factors of the large number. So to set the scale now, we can, for example, to figure out, to factorize a 150-digit decimal number, it takes about 10 to the 9 operations and roughly a few tens of thousands of qubits to perform this algorithm. And to set the scale, I mean, we can only do a handful of qubits right now and do some of the simple operations. So we're certainly way far away from that at the moment. But the basic message here is that in principle, all we need to do is do these single rotation operators coupled with these 2 quantum bit operations. For example, the pi phase gate that I mentioned. So just to try to, before I say what I'm going to do next, is to try to give you an idea how we're able to implement the elements of these required gates using atomic ions. But before I do, let me return to this Schrödinger's cat idea again. And one way to think about how this becomes closer to a larger example of Schrödinger's cat is if we think about at some instant of time we have all these 2 to the n qubits, and say at some intermediate time in this quantum algorithm, we can actually write the wave function. We can say, for example, select off the first quantum bit. It could be any of the quantum bits. But we can always write this intermediate wave function as a component that has the first bit being 0 or spin down, and the other bit being up, spin up or 1 in this representation. And then, of course, in general, we have some large entangled superposition. But the basic idea is that the wave function that represents all the other qubits associated with these first two qubits, this overall state looks very much like Schrödinger's cat in that the first qubit, you might say, is like the radioactive particle, and that all the other qubits represent some wave function, which is like Schrödinger's cat in the sense that it's now a very large number of quantum bits. It becomes more macroscopic. And in general, these two states represented by all the other quantum bits becomes macroscopically distinct. So in fact, if we could make this quantum computer, we're actually making a more macroscopic version of Schrödinger's cat. So now let me say, I'll give some ideas of how we actually try to carry out the elements of quantum computation using atoms, in our case, atomic ions. And the basic idea was that it was laid out by two theorists, Ignacio Serac and Peter Zoller, and these two theorists, Serac and Zoller, are exemplary people in the sense that they're well connected with the capabilities and limitations of the experiments. And when we all heard about this idea of quantum computation, when I say we all, I mean the atomic physicists, they immediately jumped on this idea, and they were familiar with the way the experiments in using trapped ions, and they suggested a way to actually implement a quantum processor. And I'll try to give you some of how we realized some of the basic ideas of their scheme. Well, one of the reasons they realized that atomic ions might be an interesting system is that in this quantum computer, we're trying to make these entangled superposition states. And one of the requirements is that we need to preserve this entanglement, this coherence between the parts of this entangled state for long periods of times. And one of the advantages of atomic ions and atoms in general is that we can make coherent superpositions that last for long time. So as an example, we can make two-state superpositions that have lasted over 10 minutes. This is closely connected with our work on atomic clocks. So this is certainly one of the attractions of atomic systems, as opposed to, say, for example, in condensed matter system, which there's many possible implementations. The typical long lifetimes of superpositions there are on the order of microseconds at the current time. So this is certainly one of the advantages. Anyway, so with the idea that we could use two states of an atom or an atomic ion as to form our qubit levels, one of the issues is how do you you can preserve the superpositions very well, but how do you make a quantum gate between them? And these two, in some sense, these two requirements are at odds. That is the idea of a long-lived superpositions, and gates are at odds because what you want to have long coherence times, you want the atoms to be well isolated, but in order to form a gate, they have to somehow talk to each other. So what their suggestion was, and so in this cartoon here, I show some electrode structure here. I'll say a little bit more about that in a minute, but we have some electrode structure, which you don't need to know much about, but just think of the idea that this electrode structure forms a three-dimensional harmonic well for our atomic ions. And what we typically do is we make the harmonic well along this horizontal direction relatively weak compared to the harmonic well in the direction perpendicular to this axis of the system, so that when we put atomic ions into the trap, you can think of the well along the axial direction here as all the ions want to fall to the bottom of this well, but the Coulomb repulsion holds them apart into some regular array, which is known as this linear array in this example. So the idealized version of Serac and Zoller's scheme was that you assume using the techniques of laser cooling is that you first freeze out the motion. You can think of this as kind of like a pseudo-molecule that we've made artificially with using this electrode structure. So if we can freeze out all the motion, the motional modes, their idea was, well, think about one of the motional modes. The simplest one to think about is, say, the center of mass, where the ions are all moving back and forth together. And if you think about the ground state of this motional mode and the first excited state, then this also forms a qubit. We can let that be a qubit. And so their idea was, if you can somehow take a laser beam, focus it on this ion, and if you can somehow map, say, the internal state superposition of this ion here that's selected by the laser beam, if you can now map that onto this motional state superposition, and then if you can subsequently do a gate between this motional qubit and the internal state of the second qubit that's focused upon, then basically you've done a gate between these two internal states. And I'll try to give an idea how that works for the atomic ion case. So let me just say a little bit about these trapping devices. I won't say very much about these. These rely on using the idealized structure is this 4-rod quadrupole geometry. And the way we provide trapping in a direction perpendicular to this axis is we put RF potentials, typically on the order of a few hundred volts at tens of megahertz. We apply a common RF potential to these two electrodes, and these are at RF ground. And these RF fields, since they're inhomogeneous as determined by this electrode configuration, they provide what's called the ponderomotive potential, which confines the ions along this axis. And then along the axis, you notice I made some cuts in these electrodes here, and the way we provide the well along this axis is that, well, all of our ions are positive, so what we do is we apply positive potential to these end segments relative to the other electrodes, which then provides a harmonic, to a high degree, a harmonic well along this axis. Well, one of the things is that it turns out, I won't go into all the details, but the speed of the gates that they're talking about are proportional to the motional frequencies of this pseudo-molecule. And those in turn, given all these other parameters being the same, those goes as 1 over the dimension squared. So the message here is we'd like to make this structure fairly small. It becomes difficult just to use conventional machining when we go down to dimensions of less than a millimeter. So one way we've been able to make these structures, it's certainly not the only way, and it's not the best way in the end that we think, but we've been able to do quite a few experiments approximating this structure here with what we do is we take alumina plates, which are, alumina's a good insulator, and then we gold coat this alumina plates in a way that mimics the structure here. So for example, the internal surface of this electrode we mimic with that surface there, and then the cuts in these electrodes we laser machine slots in this alumina substrates and then divide the electrodes according as I've shown here. And we take 2 of these plates and then sandwich them together with a spacer that's not shown here to approximate this structure there. So this gives one example. It's the same picture I showed briefly before. You can see we're looking down on one of these plates. Here's the cuts in the electrodes. So again, we apply positive static potential to these end segments, and then underneath this electrode here is a complementary set of electrodes to provide trapping along the axis of the system. So, okay, so let me say a little bit about the internal structure of these atomic qubits, what forms our internal state qubit system. Typically what we do is we take hyperfine states in the electronic ground state of an atom or ion, and if you don't know what a hyperfine state is, it doesn't really matter. It's for the purpose of discussion here. But one aspect of these hyperfine states is if we set up a coherence in the system that is a coherent superposition of the qubit states, they can last very long. The radiative lifetime is extremely long, so we don't have to worry about radiative decay. And in this example of the beryllium qubit, the two hyperfine states that we're selecting here, this is the atomic notation, are separated in energy represented by frequency by only about a gigahertz. And so what I've shown here in this diagram is I've shown the levels of a single qubit represented, the internal states are now represented by these spin up and spin down analogies. And then I've shown for each one of those states the levels associated with this mode of motion that we're going to use to try to couple the ions together in this scheme outlined by Serac and Zoller. And typically, these motional frequencies are separated by an energy corresponding to 5 megahertz. Now, in these experiments using hyperfine levels, in principle, we could use a single RF field to connect these levels, but we typically use laser beams, as Serac and Zoller envisaged. And the reason for that is we can take the laser beam and focus it down to an individual ion and get selectivity that way. The other thing, which is a little more subtle, is that what we'd like to do in general is we want to, say, drive transitions between the qubit states that not only change the internal state, but, for example, would change the motional state. And to do that, we need strong field gradients, and we get those with the laser beam fields. So just to come back to the requirements, remember now we want to, in principle, all we want to be able to do is to do these two types of gate. The so-called rotations is the first ingredient, and to do that, what we do is we tune the difference frequency of these two Raman laser beams. What we do is we tune the difference frequency between these two beams such that it matches the internal state, the spin flip frequency, but leaves the motional state alone. And what that allows us to do then is it allows us to invoke this rotation operators. That is, as an example, we can take any state and spin down and in the nth motional state, and then generate this superposition here. So this allows us to implement this rotation operator. And the reason that's important in the Serac and Zoller scheme, you remember the first step we needed to be able to do is we needed to be able to map the internal state of one qubit onto this motional qubit. And the way we do that is we just tune the difference frequency of the Raman beams so that it takes this component of the wave function and maps it down to here. So in effect, if we've done this mapping now, this qubit that we're focusing on, we take its internal state superposition and transfer it on to this motional state superposition. And then to perform a gate then between this motional qubit and the other ion, we're going to select by focusing the laser beams onto that ion. We use a trick here where we're going to use some other internal state of the ion, and in fact, this is another hyperfine state of the beryllium ion in this example. And to realize this so-called pi phase gate that I briefly outlined before, all we do is we drive a coherent transition that seems like it doesn't do anything. It takes this amplitude here, drives it coherently through this state here, and then comes back up to here. But if you remember, if we take say, spin 1/2 particle and rotate it by 2 pi, what happens is that we pick up this pi phase shift. We pick up a minus sign in front of the component of the wave function. So when we implement this gate here, we're able to actually realize this logic, this truth table that we needed to implement this quantum gate. So this is the scheme that, so we've actually, in some sense, we've satisfied our requirements now that we need. We've done this rotation gate, and with this operation here, we're able to make the pi phase gate between two selected qubits. So you might say, well, our task is done. Of course, we don't do any of this very well, and in order to make a quantum computer will have to do all of these operations a lot better than we do now. So finally, let me say at the end, if you'll remember in the example of Shor's algorithm, we do all these coherent manipulations on selected qubits. And then finally, what we want to do is read out the states. That is, we want to collapse the wave function for the internal states of these ions. And in atomic physics, we have this nice method that applies to a lot of systems where we can use another laser beam, and in that case, we can scatter light such that when we scatter light, say off the spin-down state in this example, the atom has to return to the same state. And why this is interesting, this so-called cycling transition, is that we can scatter many photons, even though we may not only collect a very small fraction of the photons. We can collect enough of them to determine that the ion is in this spin-down state. If the ion was in the spin-up state, then we realize a situation where there's very little scattering. So in any case, we can, with high efficiency, detect which state the qubits are in the final measurement process. So I've said that using this scheme of Serac and Zoller, we can start to implement these basic gates. And so what we want to think about now is how we might scale this system up. So in fact, we can, in these traps, although my cartoon doesn't indicate it here, we can actually, in these trapping structures, we can actually store up to millions of ions, and we can crystallize them into this pseudo-molecular state. The real problem is that I've explained the gate operation in terms of us being able to address one mode of motion that we isolate. And the way we isolate it is that all the modes of motion have different frequencies, and we can spectrally isolate the transition when we do, for example, if we go back, when we do these transitions that drive, say, the internal state and also change the motional mode. The problem is that this one is, say, around 5 megahertz, and all these other modes, they have different frequencies, but when we get to very large numbers of ions, the spectrum of these modes becomes so dense that we can't reasonably isolate the single mode that we want to be able to isolate. So what we think about now, I think all the groups working on ions think about a situation where what we want to do is we want to make some arrays of these ion traps. And the idea we're pursuing is that we'll have this shows an element of this array where if we want to perform a gate between two ions, say these two ions here, we'll have selected them from some memory units which may be spread out through this array. And we can move them around by what I indicate here. These are segments of these electrodes that are split that we can apply potentials to say, select off ions and move them preferentially into another zone. And the reason for doing that then is that we have a fairly small number of ions in any given zone where we want to implement these gates. That allows us to spectrally isolate the mode we want. Of course, we also, when we move these ions around, they may heat up, and the ideal gate, if you remember, we want to have the motion totally frozen out. So what we think about is having some other auxiliary ion. In our case, it's magnesium ions that we freeze out the motion with this ion, and then by doing that, we preserve the coherence in our qubit states. So this is the basic architecture that I think most of us are thinking about. And to give you an idea how that might work is that here we show some simple elements of this multi-zone processor. This shows again a linear trap. This very similar to the one I showed before, except you can see there's multiple cuts in these electrodes. So above each one of these segments here, we're able to confine ions to these separate locations. And with this linear geometry, we've been able to carry out some basic elements of the idea of moving ions, say, for example, if we entangle ions over here, we can separate off one of those ions and move part of the entangled pair over here, and if there's another ion here, we can do some bootstrap operations. So we can start to be able to do this, implement the basic features of this ion array, and this shows the device we use for that. So I would, if I had more time, I would like to discuss some of these sort of simple, what you might regard as subroutines in an information processor. And I give you some examples of these subroutines that we've been able to do. The one that got the most attention was quantum teleportation, and mainly because of people associate that with Star Trek. The difference here is that we're not teleporting matter between locations, but what we're able to do is we're able to teleport quantum states between two locations. The idea being that in this final processor, if you think about this large circuit board that has our quantum bits, we'd like to be able to transfer the quantum bit information to one location in the processor to some other location. And it turns out with this scheme of quantum teleportation, we're able to actually transfer the quantum bit superposition information across this processor with only 2 bits of classical information without actually transforming, without actually physically moving the quantum bit itself. So these various kind of subroutines you might think of are all elements that would go into a larger processor. So anyway, we are, as I say, I think all the groups working on this trapped ion scheme are trying to think of ways we might be able to make larger arrays. I show this is, again, the trap that we use. These are some other examples. And certainly we'd like to be able to go to some sort of monolithic, more monolithic construction. Here's a trap that Chris Monroe's group has made using gallium arsenide, and this can all be made using the typical techniques that are used to make electronic circuits. Here, for example, we've also made one using boron-doped silicon. Silicon's nice because it can be easily chemically machined to make various structures. This shows a trap down here that shows a larger array. This is a little hard to see, but this trap here made by Chris Monroe's group is a T structure. So it's starting to be a 2-dimensional array. You can also see that one of the problems we face in the future in this still relatively simple structure, which has 9 zones, you can see the wiring problems we're going to have. So this, certainly as we scale up, we're going to have to attack some of these more seemingly mundane issues is how we wire this thing up. So one of the things we've been thinking about, and other groups now are too, is how we might simplify this physical structure in order to be able to scale up. And so what I show in this diagram, if you think about looking down the axis of these 4 rods that comprise the trap structure, it turns out that we can deform these electrodes into a plane, and in fact we still get an axis of trapping looking down the system, where we get an axis above this planar structure. The reason this is nice is that it's much easier to do microfabrication of electrode structures in a plane than some 3-dimensional structure which we originally used. Actually, for those that are familiar with it, in the atomic physics experiments, this is essentially just the electric analog of the magnetic traps that people use for neutral atoms. But anyway, this is nice because we can more easily fabricate these structures, and this just shows a few examples. This is an example of a single zone device we've made on in this case it's quartz gold electroplated onto quartz. This shows some other examples I won't go into, but there's certainly various combinations that could be used. But the nice thing about this is that once you make one device using lithography and plating techniques. You can make lots of zones. So this is something we're working on right now. So for example, this is kind of a ring structure here where it has 200 zones, and we haven't demonstrated this yet. But the nice thing is as I say, is we can make 200 zones just as easily as we can make one, and we're trying to utilize these structures in the future as we go to larger, as we scale the system up. So let me just briefly say, I've mentioned I've centered this talk around ion traps, but there's many other physical implementations people are thinking about. Certainly, people look a lot towards condensed matter systems, solid state systems, because a lot of the infrastructure is there for making these structures. And one of the, so for example, people are thinking about using Josephson junctions as qubits. There's so-called quantum dots, and I'll give one example of that. There's other schemes here, and probably many that people haven't even started to think about here. But let me give one example. This is a system that several groups are working on. This picture here is from Charlie Marcus's group at Harvard. The reason I like this one is just that there's a fairly direct analogy to the case of trapped ions that we're working on. And in this case, they have electrons that are confined to two dimensions, so-called two-dimensional electron gas. But what they're able to do is actually using an electrode structure which is printed on top of this structure, this two-dimensional electron gas structure. They're able to again, very similarly to the way we do, they grab onto the charge of electrons, and they're now able to take single electrons and to put them to localize them in these electrode structures. And they're able to start to make some crude atomic gates. So there's actually a lot of commonality, even though this is a condensed matter system. And I might say that this looks very much like our ion trap scheme, and the difference is that here their ions, the electrons, are actually inside the host material, and they're able to, because of that, and because of the smallness of these structures, the potential speeds in these devices are very high compared to what we're able to realize. But one of the problems they have to deal with is because the electrons are in the host material, these electrons are seeing the environment much more strongly than we are, so that the decoherence times are typically, I don't know what the best is right now, but they're typically less than microseconds. So they have to do things very quickly if this device can actually be used in the future. So let me just say, I'm going to conclude by giving you just one example of how we're able to apply some of the simple ideas that we've been able to use in quantum information in metrology. And for us, metrology, the interesting thing is to make atomic clocks. And these days, one of the atomic clocks have now gone to the optical regime. And let me just say briefly, give you the 1-minute version here of atomic clocks. Basically, all atomic clocks work essentially the same way. We find some atom, we find a transition that has good properties, and what I mean by that is its frequency of the transition will be fairly immune to external influences like electric and magnetic fields. And then what we do is we have some oscillator, and nowadays it's a laser, but it could be a microwave oscillator, for example. And what we do is we drive this transition, and all we do is we look for the condition where we drive this transition with maximum probability, and then when that condition is reached, then we measure the frequency of this oscillator, we count cycles of the radiation to generate a time interval. So all clocks work essentially the same way. The thing that's interesting these days is we use very high frequency transitions, optical transitions, and the reason for that's interesting is that we're able to count more cycles in any given measurement time, which increases our measurement precision. So we've known about this to give a little history on this. I mean, the atomic clocks ever since they were invented in the early 50s have been based on microwave transitions. For example, the so-called hyperfine transition in cesium. And we've known that this idea that we'd like to go to very high frequency to count more cycles in any given measurement interval. The two impediments to why it hasn't been done before the last few years is that there were two main technical problems. One is that although we were able to think about many atoms and ions that had very narrow optical transitions that would provide a good reference, the first problem was that the lasers weren't stable enough. And in our lab, Jim Berquist a few years ago was to make lasers that had a line width of about 1/10 of a hertz averaged over a minute or so. And in fact, he still holds the record on the spectral purity of lasers. So that was one of the requirements that was needed. The other one was is just, I mentioned in the simple example, what you do is you synchronize the laser oscillator with a transition, and then you count cycles. Where this counting of cycles was not practical until the last few years when these frequency combs were realized, which essentially act as a frequency counter. So the Nobel Prize of a couple of years ago, shared by the part shared by Jen Hall and Ted Hench, was the realization of this frequency counter for optical frequencies. So now these two ingredients have been realized, and we're able to start to make optical clocks. So in this particular example, we were using aluminum, and the way we typically measure transitions is just how I explained how we measure the qubit transitions. We find some other transition where one of the states will fluoresce, scatter light strongly, and the other one won't. But it turns out in aluminum, those transitions, these so-called cycling transitions, are well into the UV where there's no lasers available. So what we've done here, and this is primarily the work of Till Rosenband in our group, is that in the simplest version, we've taken this aluminum ion, which has this nice optical transition, and we've also stored at the same time our beryllium qubit ion. And the idea then is, since we can't easily detect when we've made transitions to this aluminum clock ion, is what we do is after trying to drive the transition, in general, this clock, the two clock states will be in a superposition state. We first map the superposition state onto the motion, just as I described before, and then we map that motional state onto the beryllium qubit, which we can easily detect. So it's a way to use some of these simple ideas of the quantum computation scheme to be able to detect aluminum ions. Another aspect of this is interesting by itself, but it turns out when we do this mapping and detection process, it doesn't change the probability of the probability amplitudes for these two states. So we can actually repeat this mapping and detection process and improve our detection efficiency. And in fact, in this experiment here, we do multiple transfers each time we drive this clock transition, and we can go from a detection efficiency of about 85% to over 3/9 efficiency by using this so-called quantum non-demolition detection. Anyway, there's some features here that we weren't appreciating on the front end. One of the nice things, for example, is that it turns out that the beryllium ion is much more sensitive to electric and magnetic fields, so we can measure the local electric and magnetic fields by actually measuring the beryllium ion and then inferring what they are on the nearby aluminum ion. The other thing, the punchline here, is that these clocks now, we have in our lab this aluminum clock, and Jim Berquist, who I mentioned, has developed a clock based on mercury ions, and and the performance of these clocks are such that the stability of each clock is in this range here. This is only important for, or I apologize to some of the people in the audience. This is what this number represents is the frequency fluctuations of measurements between the two clocks expressed fractionally. So what this represents, tau here, is the measurement time. So at 1 second, it means that the frequency fluctuations between these two clocks normalized by their frequency, divided by the frequency, is about a part in 10 to the 15. And what we're most proud of is that now that both clocks have a systematic uncertainty of about 3 parts in 10 to the 17, which is about 10 times lower than the best cesium clocks, which are currently representing currently realize the second. So let me summarize and just say just a few concluding remarks. So I've tried to say how we've done some of the basic operations, at least the required elements to realize a quantum computer. And I've tried to indicate where we're heading next. We're trying to make these multi-zone traps with the idea of scaling up to larger numbers. And I've given an indication how we can apply some of the simple ideas to metrology, in our case, atomic clocks. Of course, the real message is we need to do everything a lot better. The fidelity, or you can think of this fidelity number as the error is basically 1 minus this number. In order to do a realistic large-scale computation, we need to reduce the error by about 2 orders of magnitude more than what we're able to do now. And at least the good part of this is that I mean, this is not a fundamental problem. That is, we just need to control things better. For example, one of the problems we fight against all the time is just being able to control the intensity of the ions, intensity of the laser beams at the position of the ions. And we have to do a lot better job on that. And it's not to say that it's easy, but at least there doesn't appear to be any fundamental problem. Of course, as we build these larger arrays, we have to think about how we might multiplex various things. The lasers, for example. This picture here shows this. This will not impress any of the atomic physicists here, but our quantum computer is this little tiny thing hidden over in one part of the lab, and we're totally dominated by all the laser beams we need. In fact, in this particular experiment for our beryllium ion quantum processor, we need four ultraviolet laser beams coherent ultraviolet laser beams that we switch and frequency shift in various ways, and that's what all this hardware is here. So now as we scale up, we're not going to need to scale up all this hardware, but we're certainly going to need to scale up the number of laser beams that we manipulate separately. So, and there's also, I mentioned the problem of just the leads going into these arrays of ion traps. This surface electrode geometry helps a lot, and for reasons I won't go into here, but that'll help a lot. The other thing, let me just mention one practical problem. I've sort of given the optimistic view of things here in the sense of I've only focused on the kind of the accomplishments, but one of the dirty details, and there's many, I try to indicate here. One of the things we fight against is that I mentioned that the quantum gates are such that we'd like to first freeze out the motion, and then we do this mapping procedure and so on, as outlined by Serac and Zoller. But one of the things that hurts the fidelity, hurts the efficiency of these gates is if the ions start heating up, if the motion heats up, then we scramble these the motional quantum states. And the biggest problem we have, the most annoying part of this heating problem, is we don't understand where it's coming from. For example, one source you might think of is that in these electrodes, there's some resistance in the electrode material. There's thermal electronic noise due to that, Johnson noise, and you might think of it like as in a resistor. But the heating we see is much above that. And we have some models that seem to fit the data we see, and it corresponds to the idea that there's somehow some patches on the electrodes that have electric potentials that are fluctuating. And we're very slowly trying to understand, and when I say we, all the groups are trying to address this problem. One thing that lately is that Chris Monroe's group and Ike Chuang's group at MIT have tried to use the traps at low temperature, and what they've seen is that whatever this heating is, it appears to be thermally activated. So going to low temperature, maybe we won't understand it, but maybe by going to low temperature, we can freeze out this extra heating. So that's just one example of the kinds of problems we have to think about. So I don't know, some of the near-term goals that we think about the next few years is we hope to be able to separate or to manipulate 10 or more qubits and do some interesting things. One of the things I haven't mentioned is this idea of error correction. We will have to invoke some sort of error correction, and this is another interesting topic by itself. This idea of error correction sounds kind of strange at first, but it turns out that we can, if we encode a single quantum superposition, a single qubit in an intelligent way into several qubits in particular entangled states, it turns out that we can recover from decoherence. That is, one of the qubits in this entangled superposition, this so-called logical qubit, can undergo decoherence, say spontaneously emit a photon. And it turns out that these ideas of error correction allows us to recover the superposition state that was encoded into these multiple lines. So to be able to do that, we've done some simple demonstrations of this for certain kinds of errors, and we want to do it to be able to handle our errors. So that would be really one of the kind of landmark experiments to be able to correct all types of errors in quantum superpositions. And then finally, I say, well, maybe we'll be able to make a useful quantum computer in the future. And I say, or not. And the reason I say that is that it comes back to this idea of Schrödinger's cat. I mentioned that in Schrödinger's algorithm, we're kind of making a larger version of Schrödinger's cat. That is, this large array of quantum bits has the same characteristics of Schrödinger's cat. And it comes back to this thing that bothered Schrödinger. That is, why don't we see Schrödinger cats in our everyday life? And it's because superpositions are very fragile, particularly when they involve a large number of particles. But as far as we know, there's no reason we can't make these kind of Schrödinger cat systems. But I think that it's such a perplexing problem that, for example, some people have said, well, maybe there's some sort of fundamental decoherence that doesn't play a role when systems are very small, say a few atoms, a few qubits. But when we go to larger systems, there may be some kind of decoherence mechanism that comes in that prevents us from making these larger entangled superpositions. So actually, one thing is that our work is funded by the National Security Agency, the spies that want to be able to crack codes. Well, they would really like this answer. That is, if there was some fundamental decoherence mechanism, they would be happy because then they know they couldn't make a quantum computer, and so they could go happily on using the classical codes that they currently use. The bad part about that is it put us out of business, because if we found this decoherence mechanism, then they wouldn't be interested in making a quantum computer. So, but anyway, to give you an idea of why, at least I think a lot of us feel that there is some fundamental issue to be found here, is that, which is called, some people sometimes referred to as the measurement problem in quantum mechanics, is that, so for example, think about the following system. We have some quantum system. Let's say, think about the clock example. The quantum system will be this aluminum ion that we can, when we drive the clock transition, we make a superposition state. And the detection apparatus in that example will be this beryllium ion that we map the superposition state onto, and then we scatter light from. And of course, we know what happens in the lab when we do this experiment and we connect these two systems together. On any given experiment, we'll find that the atom was in the one state, let's say the excited state of the aluminum transition. Well, kind of to get an idea where the problem comes back is that we think about our quantum system, in that example, the aluminum ion, and the detection apparatus, which is this beryllium ion. And in fact, this is another, it's just a larger quantum system. And in fact, when we do this mapping between the aluminum ion and the beryllium ion, we can undo it. That is, this system is coherent until we apply this laser, which decoheres thing. But the real message is that the laser is just some other quantum system. Admittedly, it's a big one, but where, the problem comes back to where is this dividing line that allows us to talk about when things are collapsed into to certain states, and we really, I would say we really can't determine that now. And to emphasize that, you can think about the larger problem. If you think about this as a quantum system, us as the observer, we're just another quantum system, a larger one, but is this system coherent now? Obviously, we don't think so, but where is this dividing line? So this is an interesting problem that maybe we'll stumble on and be able to find the answer to, or at least lend some sort of resolution maybe to this problem. Anyway, with that, I'll stop. Thanks.
I particularly appreciated your final comments about the role of the observer in the system, because it is very unsettling to me. If you try to replace your observer there with a machine which observes, it isn't really an observation until somebody knows about it. Right? It becomes, at that point, the system becomes irreversible. Right? And you ask what you mean by knowing about it, and it means that you're conscious of it. Somehow the human consciousness seems to be working its way into this. The interface between the quantum world and the world of consciousness is somehow important, but very unsettling. I mean,
I can only agree with you that it's very unsettling. I mean, so I would say, I think most of us are in the camp that there is, I think there's some fundamental problem in our thinking about this whole measurement issue, and at some point consciousness comes into it.
yeah. Okay, so we'll just leave it at we're both unsettled.
If anybody has any good
maybe somebody
ideas,
there can resolve the problem sometime. What you need, of course, is a quantum mechanical theory of the brain.
Yeah.
And it's not at all clear that such a thing could ever exist.
Well, I can tell in my case it's totally incoherent, my brain.
Could you comment a little bit on the Divincenzo criteria as applied to this system? In particular, these last two that he added about the flying qubits.
Okay. The reason, what the question refers to, there's a so-called Divincenzo requirements, and I think I just briefly mentioned those at the top of this list here. Well, anyway, these required elements were first outlined by David Divincenzo. The first five have to, maybe I won't get them all right here. Basically, you want to be able to make quantum gates. You want to be able to have a system of well-defined quantum bits. You want to be able to do efficient measurements and so on. The last two that the question refers to have more to do with quantum communication. That is how you would, and this is a subject I really didn't touch on here, but the one aspect of quantum information processing is to be able to do quantum communication between remote sites. And the last two requirements of David Divincenzo refer to quantum communication systems, where you want a transformation in over large distances. And that, I would say, in some sense, we address it here, but only on a very local scale. We want to transfer information over the size of our ion processor, but technically it's quite a bit different than when you're trying to transfer information, say, by 100 kilometers. And so I think it's more, those last criterion that he added were more to realize a practical quantum communication system over large distances. So it's really the first 5 that are more relevant for the quantum processor, and that's really all I talked about.
About your array of ions, when you build your trap, you put they are essentially the same distance between
no,
diet,
they're
or is
they're
there
not exactly.
some fluctuation?
Well, there's when at low temperature, in other words, when they're frozen out, then the fluctuations are gone. But actually, the spacing is not equal. It turns out they're more the spacing is a little wider on the end when they're confined in a harmonic trap. That particular aspect doesn't appear to be a limitation for the things I talked about.
But it affects your computation when you do some the gates, the quality of the doesn't affect.
It turns out, well, I mean, we have to take into account the geometric arrangement, but the basics of what I talk about, this unequal spacing doesn't really affect the general scheme.
Part of magazines about the problems, the main challenges in building a computer based on mechanical quantities. And do you really think it's possible to build a computer based on mechanical quantities?
I'm sorry, based on what? I'm sorry.
On the mechanical and quantity mechanical.
Oh.
So like in Scientific American, there is some actors that says that it's almost impossible to build some kind of device.
Well, I think my answer would be the same as a lot of us thinking about this problem. Is that I think as far as we know, that there's no fundamental reason that we can't make one. I mean, in the same breath, we have to say, I mean, certainly the technical problems are very hard. But I think, the optimistic thing to say, and I actually believe this is, I think it's where you think about it, where, all the physics experiments are done. I mean, the vast majority are in this area of trying to control quantum systems better and better. So I think at some point, may not be trapped ions, it may not be any of the schemes that people have thought of yet, but I think we can be optimistic that eventually we'll be able to control these systems well enough that we will be able to make such a device. And this is, I mean, I'm on safe ground here because I can say it's certainly technically hard enough. It won't happen. It's unlikely it'll happen in my lifetime, but I think we can be optimistic about it happening. And having said that, I think one of the things, the thing that really got the field going was this Shor's algorithm, and certainly that provided the money because of the interest in the government wanting to protect secrets and so on. But I think what most physicists look for is a system, it'd be a smaller version of a quantum computer. And this goes back to Richard Feynman was one of the first people to think about ideas of quantum computer, and his idea was, his application that he thought of was to have one quantum system simulate another quantum system. So that, for example, I mean, I don't know what exact numbers are, but for roughly 20 or 30 qubits, if you try to handle all the superposition state based on you don't have enough computing power in a classical computer, but certainly if you could make your a 20 or 30 qubit quantum computer simulate some other quantum system, that would be very valuable. So I think most physicists think that, I mean, Shor's algorithm is extremely hard, extremely demanding problem, but perhaps with less than 100 qubits, you can really do some interesting physics simulations. So I think that's I think that's where most of us think the first real application or general application will occur.
I have one more question. It's a very interesting question about the teleportation of information. Information is limited by the speed of light. So
Right.
we don't teleport information. We teleport wave function. Is
Yeah.
that
Yeah,
for real?
yeah, we're not, certainly in this idea of quantum teleportation, you're not we're not doing superluminal communication. I wish I had time. I mean, it's a very interesting algorithm to go through, and wish I had more time to talk about that. But the reason it's not superluminal is that in order to carry out this quantum teleportation, you have to transfer some classical information between the two sites, and you're limited by the speed of light there. So it's certainly not superluminal.
Okay, there is a very interesting theory about by the physicist John Magage from Imperial College from London, and he said that the speed of light varies through time. As you go back to the past, the speed of light becomes higher and higher and higher. What do you think about such a theory? It has something to do with entanglement. So, because we know if we go back to the Big Bang, let's say, the speed of light was infinite. So we don't need, for instance, to have inflaton field, like he.
I see. Well, I don't know the paper, and I mean, it sounds like an interesting idea, but it's probably not so practical for us to think about. I can't comment about that, I'm afraid.
Because if you have some infinite speed of light, it would allow the information to come from one place to another instantaneously, you know.
Well, I'd say we have enough problems to solve right now with it.
We have a possibility to calculate the, in case of classical computers, the limits of channel capacity using the Shannon theorems. In the case of the computers, quantum computers, can we calculate this channel capacity, the quantum channel capacity?
Yes.
And what kind of impairments applied in this case?
Yeah. First of all, I'm not expert in this problem of channel capacity, but there's certainly a mapping of all the ideas about channel capacity that map onto the quantum world, and this. I mentioned one example we've been able to do is this so-called dense coding, where you can show that with a quantum system you can increase the channel capacity beyond the classical communication capacity, but that's another whole other subject. But anyway, I should say I'm not expert in this, but there's certainly a lot of people are thinking about this connection between classical channel capacity and quantum channel capacity.
So we would like to thank you, David, for coming to São Carlos. For us, it's a very great pleasure to have you here. And it was very nice to hear this wonderful talk. And I'm sure that everybody has some question about quantum computing. It's so many things we want to understand that we don't. So we appreciate your talk. We appreciate your visit to São Carlos. And please let's thank again David for the nice talk.